elaborate it further, and some of his influences on this work you will see, because we share the passion for modeling the human. So, what I will tell you today is my more recent passion, and that is what I'm hoping to accomplish in the next few years, is to have a framework where I can bring any of us into this framework and take measurements without hoping to do anything, just external measurements, and get parameters so that I can create a model of kinematic, how far can you reach, and let me tell you that this is not a trivial problem for some people who have muscular dystrophy, who cannot do this or cannot do that. So workspace, using the jargon of robotics, is very important, and that comes from kinematics. But then we hope also to have estimation of dynamics of your capabilities, which will tell you how heavy objects can you lift, how much can you manipulate with objects. Now, the side effect of this hopefully will tell you how stable you are when you are walking, and Aaron has been working on that much more than I have, because stability is a big deal, especially as you get older. People fall, and because their bones are rather frail, it kind of crumbles. It's not even breaks, but it crumbles. And so for older people, and you all will get there, believe me. That's one place where the Mother Nature is very fair. We all get old. And it really is threatening to many people. So stability of having to stand or walk is very important. And as I said, estimating the parameters about your kinematics and dynamics should help to predict whether you are more prone to falling or not, whether you are able to do certain activities. So let me just continue with my presentation. So motivation, as I said, humans interact with cyber-physical systems. By the way, some of you may not know this word cyber-physical, meaning physical is physical. You know, I'm holding something like a cup or even a deformable object. That's physical. Cyber is when we put the information technology into it. Scenarios span many levels of complexity, from simple tasks, specific communication, to complete dynamic interactions. We wish to understand the mechanics of these interactions and the design of algorithms. And the design is not only finding all these parameters, which sometimes require certain signal processing because some of the measurements are noisy, but also control algorithms, how you control in order if you have some problems, how to give you a feedback. We will illustrate these on several examples. So, why is this problem important? A person is a complex kinematic dynamic system. I was meeting just before this with a bunch of some of your students who are here, and they asked me, why I am doing what I am doing. And the reason is that I cannot grow into your head. Okay, now maybe with some of the future technologies we will have better way of reading your thought, but for now, I don't know how to do that, and I don't think anybody knows. And it's not obvious to me that actually it's always desirable to know what you are thinking, because it can be abused and misused. But anyway, be as it may, this point, I don't know how to grow into your head, and therefore, the only thing I can model and build some systems is about activities that I can observe. So the only thing I can do is observe your kinematics and dynamics and extract these parameters. So the central question I'm posing is, what is the appropriate representation of human physical action for specific applications? Is there a systematic way to detect and classify what appropriate sparse representation, and I will explain why sparse representation is for a given class of activities. Sparsity is important because you can measure a lot of things and get a huge space of parameters. But to evaluate that in real time, that you won't really have, is not very practical. So besides, sometimes over-parameterization might give you the wrong answer. So what features should be used? What should be generalized coordinates? What kind of coordinate system you want to use? So here is a kind of the agenda that I am kind of pursuing. So this it kind of goes from more concrete to more general. Anyway, this is the picture of the agenda. So human model classes agent interaction is model human interaction with the system using a simple application-specific set of observed variables. So for example, driving is a very nice application because you are, in some ways, you cannot do too many things. So you are constrained what your body can, how the body can interact with the machine. And remember, car is a machine. Furthermore, the control problem of the car driving on the road is relatively simple, and you can model it as a two-dimensional problem. So in that sense, it's a relatively simple problem. So example of observed variables: hands on steering wheel, driver looking out the windshield, driver away. So we want to, in this particular project, we want to observe the driver, how attentive he or she is, and if they are not attentive, by texting, which we can detect by observing where their hands are, where their arms are, or even with their eye movement, whether they are really looking at the road. We can then automatically switch the control of the car for an automated driving capability, but only as long as it's necessary. So we maintain that we don't want to have completely an automated car. I know that there is more and more push right now for automated driving, automated car driven by automation. My personal feeling or prejudice is that this will not happen for another 10 years. And partially it's the legal issues. The legal issues are such that if this automated driven car gets into a car accident, who is responsible? Is it the hardware designer? Is it the software designer? Is the sensor? Is the computer? Who is responsible? And so for now, it seems to me that the human driver is responsible. So the big question is, if we have an idea of state of the driver, can we develop more intelligent active system, safety system? Remember, in this transportation domain, the key issue is safety. Okay? How can we guarantee that these cars will be safe. So here is how to guarantee safe interaction between driver and autonomous car that can be trusted. How will autonomous car handle heterogeneous environment? Imagine that you have, I had a car, excuse me, for 11 years. I'm not going to give it up just because there are going to be these automated driven cars. So here comes Ruzena, Bajcsy in the little BMW. And then next to me is this automated driven car. So these are heterogeneous environments. And how do I communicate with this autonomous car? And how the autonomous car communicates with me? So imagine that I want to go to the right lane where the autonomous car is because I want to get out. Well, the autonomous, I want to send a signal to the autonomous car, hey, I want to get to the track. Now, the current situation is I just put on the blinker, and the other car will see me and will respond or not respond, and my eyes will tell me, can I go to the right lane or not? In the autonomous car, this is not so trivial. So these are the issues that I want to investigate. It's a beautiful topological problem, actually. So we have a simulator, which is here on the slide, which is quite expensive simulator. It's really Shankar Shastri for it. But we can study these different environmental scenarios. So if you think about the problem, human with cyber physical system, the transportation offers a very interesting and plausible environment to study this problem. On one hand, the control with the car is much simpler than anything else you can imagine. On the other hand, the challenge comes from the environment. The environment is much more difficult. So this is the driver modeling overview. We have done experiments where we are measuring, the kinematics of the driver model, of the driver upper torso and the hand, but we also measure the eye, and then using dynamical systems, we can predict for 2 seconds or so where we want to go and what is the trajectory. And what you see here is that we can, on the right side, you can predict that if I'm supposed to drive straight, that what is my tolerance, what are the boundary conditions that I still will be safely driving, okay? So these are, and this comes out from my dynamical model of the car and how I'm driving, assuming that I'm driving straight ahead. Now, if I have a scenario that I have to change lanes, then of course I have this problem of communication, and then I have to do this strategy, and those green things gives you the possibilities that come from the trajectories, that what your possibilities are. But then if those green regions intersect with the other car, how it's going, then that's the region where we don't want to go, which is dangerous. Okay, so we now move to the modeling of the human kinematics, and that is relatively simple. Well, now it looks simple. When we started, it wasn't so simple. One of the problems of kinematics is that whenever you put markers in order to measure the change of your motions, the markers will move because your skin moves as you are moving your joints. So you have to be very careful how you put these markers, how many markers you put on, and you still need to do some filtering, typically Kalman filtering. So in order to test some of these ideas, we have created a database of different activities, and in order to really try to understand how to model this kinematics. And what I will show you, okay, so now you can see that we have these 12 different activities, and we capture them with this motion capture system. Now, let's see. So, okay, never mind. So the main idea here from studying these different activities was that you can see from the motion capture where we put the markers. So you have seen the markers. And one very simple insight that was validated by this experimental data is that depending on the activity, not all joints are energized, are used in the same way. Okay, so for example, if you jump, you are using your legs, but you also use your hands. If you just punch, you just use your upper extremities and so forth. So by measuring, by computing from the measurements, computing the energy expenditure of each joint, we were able to order the different joints, and we call them the most informative joints. It turns out that this is a very useful ordering because it reduces your enormous data. As you can see, 25 different joints, it gets reduced to 4 or 5 to the most important. And so you are able to use these most important joints as feature vectors that will give us a very nice, clean classification of different activities. So this was that. Okay, so here is the feature selections. We convert the time seriously in the positioning to joint angles, in partition action sequence, in a number of congruent segments, compute the variance, etc. And then you can do it like this. So here is a time sequence of the, and I don't think, yeah, but it shows you, oh, thank you very much. That's very kind of good, that's what I mean. It shows you that even as you are doing some activity over the time, the most important joints change. So you have to do some segmentation, and this segmentation depends on which period of time during this sequence of this activity, which joints are being used. So here is the most important joints, and as you see on the right side, you see all the different activities that we have tested. On the x-axis, we have the number of joints, and what you see, the dark points will tell you which of the joints for different activities are more energetic, which then gives us the classification capability. All right, so the results gives us very reasonable results, and we published them. Okay, so in the meantime, it turns out, ladies and gentlemen, that we have faced this problem of over time for given activity, even if you repeat the activity, how can we do the segmentation? And I know those of you who work in computer vision will probably appreciate that segmentation is still an open problem. How to do segmentation automatically. So this last year, this is our more recent result that it just has been submitted for publication, is that how do we go? So we are dealing with repetitive exercises, as you saw, when they were jumping around or punching. And the question was, how can we find an automated system for segmentation? So here are a couple of slides from this very recent work. As you can see, it's non-trivial. And the reason for that is that you can come up, we use the most informative joints, but you can come up with over-segmentation or under-segmentation. And so what you really want to find out, where there is a real breaking point. And this breaking point cannot be just by session. It has to be by some physical difference, okay? So that's the whole idea. And we use the unsettling Kalman filter and so forth and so on. So anyway, here are our representation. You can see the shoulder position, the elbow joint position, the wrist position, and then we model, because the shoulders are mostly rotations, so we model them by quaternion. Some of you may know what it is, but it doesn't matter. And also the wrist, okay, is rotation, so we model it by quaternion. And so this is our representation. And then we have the UK, which is the unsettling Kalman filter, which has two steps. One is forward prediction, and then the backward validation. And using all this, we get, and then we also use the Fourier transform, because remember, we are looking for repetitive, but repetition of a more complex activity. So it's not just a simple sinusoidal, so you want to find the repetition of chunks of activities. And indeed, what I want to show you is that we do get a very nice result where you have this Muda prayer. This is this kind of exercise, and we find 3 different classes within the same exercise, and if you compare it with the manual segmentation and our segmentation, is beautiful. You can see that below that. So I'm very pleased with this work because it sort of solves a problem that we have in motion, especially in repetitive motion, where the segment is more complex motion, but if it repeats, you can use this technology, which is not ours, it's just an integration of different pieces. But you know, the whole thing in robotics, ladies and gentlemen, is there's a lot of technology out there. The question is, how do you use it? How do you apply it to solve the particular problem? Okay, so here are some results. There's a manual proposed and the zero crossing, which was developed by Maya Meffert some times ago, also tried to do the same thing, but not as successfully. And then also there is the Gaussian PCA, which again didn't perform as ours. So look, there is no free lunch, so that's what it is. So we achieved local segmentation. Again, good data, there is no need for training. Okay, no need for training. So general approach for different motion capture modalities, easy extension to more or less complex demanding models. Okay, so the next, how much time do I have, Nancy?
Let's say 20 minutes.
Okay, good. So let me just go faster now. So now so the kinematic approach that I showed you, which is measuring the joints, finding the most informative joints, using them for classification. We also use them for representing the workspace. And it turns out that finding that representing the workspace is a very useful tool for measuring for the muscular dystrophy people, because the muscular dystrophy people have a limited volume. So on this figure, you can see, you can see that the healthy subject, we cover, practically almost 180 degrees in the horizontal plane and in vertical plane and so forth. But with the advanced muscular dystrophy, the volume is much more limited. And so here is first time that we gave the doctors a quantitative measure of how well these or how poorly these patients are doing. And this is now used, has been applied on hundreds of patients, and the UC Davis in Sacramento. And, it's very sad because especially when this kind of disease you have in children, at age 15 or so, they die because the muscle crushes the skeleton. Okay, so now clearly when you bring these technologies to the healthcare environment, you have to validate them, and that's not trivial because you have to show that your technique will do at least as good as their old technology. Otherwise, they are not going to talk to you. So we have done that. Okay, so now we are looking at the dynamic, and this is where some of this work was done in collaboration with Aaron. I had a student, Ram Vasudevan, who's a professor now at Michigan, and he found out that actually, let's see, now maybe this comes later, so let me just go, okay, skip this. Okay, so let me just say the following. He found out that if you are moving, that moving can be represented by a hybrid system. And the hybrid system, the reason I really like this very much is because I don't know how many people know what hybrid systems are, but think about it, that whatever you have in those circles can be modeled with a continuous differential equation. So if you lift your left leg or right leg, that motion can be modeled with a differential equation. However, as you are changing left hand and left feet and right feet, you are crossing. The velocity goes to zero, and that gives you a switching mode to move to the next differential equation. So here we are. We have a toe lift, we have heel strike, toe strike. But when you interact with the physical system, there are measurements that you can detect that will give you the non-accidental rational why you need to switch to a different differential equation. So for example, the same thing with in manipulation. When I move, this is one differential equation. The moment I touch this, my velocity goes to zero. Then I lift this. This is a different differential equation because I have to compensate for the gravity of the weight of this cup, okay? So that is the idea behind hybrid systems. And there are a lot of questions, and actually, as I said, Ram worked on this and showed that you can model it and predict how the individual human can behave. And actually, Aaron has built some working robots based on the same philosophy, right? Correct. Now, there are a lot of theoretical questions, ladies and gentlemen, by this hybrid system, and one of them is stability. Can I guarantee that when I move here and I grasp this, okay, then I actually will grasp and I will not fall to the side. That's called stability. To go from one state to another, but guarantee that I will move from one state to the other. And as I said, Aaron had some results. We also, I have this student who has so far, so the way how you look at this problem is that you have what's called a reachable set. Okay? I can grasp it this way, I can grasp it that way. So that gives me trajectories that are bounding how much. It doesn't make a difference it doesn't make sense, but I can put it this way, this way, this way. So it gives me a region of so-called reachable set. All right? These trajectories. Now, the question there is, how can I guarantee that I will stay in that reachable set, that I will not go haywire? Because remember, the mathematics doesn't care about the physical reality unless you put those boundaries in, okay? And so the fundamental question here is really to guarantee that you stay in this reachable set. My colleague, Professor Tomlin, has worked quite a bit in this reachable set. This reachable set is a very general principle. We have it in driving, because if you drive this way, you have boundaries of reachable trajectories. If you go that way or that way, you are in trouble. You are going to be an accident, okay? Because if there is another car. The reachable set applies in obstacle avoidance. The reachable set applies in grasping. So it's a very generic concept, and so it's important to really get to the bottom of it. The problem is that solving this reachable set guarantees is limited at this point to a certain number of differential equations. And so if you want to model, and this is really a challenge, if you want to model a human with walking in 3 dimensions, and not only on 2 dimensions, but 3 dimensions, at least you need to model the ankle, the knee, and the hip in order to be critical. So you have 6 points, and each point has at least 3 coordinates because you are in it. So you have 6 times 3, 18 variables. You have to deal with this. And right now, my students are telling me, and I don't know, Aaron, if you have new results in this, but my understanding is that right now the limit of computational limit is roughly 8. Okay? So they are not able to go to this 18 degrees of freedom, and that's the limitation. And I have been pulling, whatever mechanical system I can use on we are stuck on this ancient degrees of freedom to assess whether we are in a stable region, safe region. So anyway, that's where we are. Okay, so this is, all right, now finally, we still have a few minutes?
Yes.
Okay, finally, I want to talk a little bit about, so I talked quite a bit about modeling kinematics and how I use kinematics. I talked a little bit about how we use invoking and how it applies also to manipulation and where we are stuck. So, but this is still quite a bit kinematics, although invoking we dealt with some benefits. So my next open problem is how do I measure the dynamical parameters of the R and of the head. So as I told you, I can put these markers and I can measure the model, the workspace. I can measure whether I can do this and so forth. But I don't, and I can measure the torques, the torques. And the way how we measure the torques, and I'm not sure if I have a slide here, but I hope so. Okay. Yeah, here. So I can measure the torques, and I will tell you how I measure the torques. We build a 6-degree arm where we can measure the forces in the torques. We put it on a force plate so we can measure how stable it is and what the forces are from the floor. And then at the end of the arm, I put another force sensor. And now I, as a human, I'm going to push or pull this robotic arm. So from reading the robotic torques, I can, with inverse dynamics, I can compute what my torques are, okay? So that is just now we are collecting some data. However, there is more to your arm. You have muscles. And how do we measure the muscles' forces? So for your information, the known measurements is that when we, as you know, in your arms, you have a bundle of muscles. It's not just a single muscle, okay? And these bundles get a signal from your brain, push or pull or lift. So how do I measure that? Well, right now, if the muscles are activated, and we put 2 electrodes in a certain distance, you can measure the potential, the electrical difference between those 2 electrodes. Now this is called electromagnetic, EMG. I lose my mind what the EMG stands for, but anyway, you measure the electrical potential there. Unfortunately, this electrical potential is quite noisy. So I have been looking for other way of measuring these muscle strengths and forces. And in the literature, you will find another phenomenon that when the muscles are activated, they apparently vibrate. So you can put a microphone on your and measure the vibration, which then can be correlated with forces. However, I find a very fascinating other approach, and that is using ultrasound. You can have like if you are pregnant, you go to doctors, they look at your baby through ultrasound. Similar technology can be used for measuring the strength, the activation of this muscle through this ultrasound imaging. So I'm hoping to investigate it. We haven't done it. Anyway, challenge is, ladies and gentlemen, how to measure non-invasively the muscle strength. And it is certainly non-trivial. But if we have that, and once we have that, then we have a parameterization of the dynamics of the human body. And that is critical, not only to understand how to design assistive devices, how to design exoskeleton devices, but it's also critical how to design the cooperation between the robot and you as a user. Because if the robot knows your model, then the robot can simulate that if you are lifting something and it's too heavy, how much it should help you. And this is quite critical in any cooperative system for human and robot. So, okay, so here is some how to optimize the existing framework, and you have here some descriptions which I'm not ready to elaborate on. Compute workspace using levels and methods to find statically achievable points. Okay, all right, so open problems. Big question, how to communicate intent to cooperative human autonomous system, industrial either in transportation or in assistive technology. Analytical and computational tools cannot handle the complexity of detailed human kinematic direction model. Therefore, we are looking for this subset of person musculoskeletal parameters need to be known for a given task. Now, different tasks, they need a different detail. Okay? So hopefully we can deal with that. Okay. And so here are my collaborators from UC Berkeley. Between muscular dystrophy, we collaborate with Oregon, with the Jay Han from UC Davis, and on the information with Ruzena Vidal, and of course MSF has been very kind to us. So thank you very much. Yes, please.
The beginning of the talk, you talked about how agent can help a human once the human becomes
Yes,
older.
yes.
How can you guarantee the integrity of the agent? What happens?
How can you what?
Guarantee the integrity of the agent. What happens when the agent becomes old?
The agent becomes faulty. You mean the human?
No, no.
The robotic agent. Good question. I haven't thought about the, the robots are perfect, right? It's the humans who fail, right? Well, I'm kidding. We haven't solved that problem. So, I think the current work that Aaron Besky, my student, is working on is more how do I communicate my intent to the robot. Now, the model of the robot is not too difficult to get. We know how to do that, right? To get that music. So that's simple. The question is that when I lift a heavy object, okay, I as human, can the robot figure out where I need the help? Okay, so for example, I killed, so those are the issues we are trying to figure out right now with respect to, you have to model this problem in a task space so that you can figure out what the forces are and where the robot has to compensate so that you have equilibrium. I haven't thought about, or we haven't thought about what if the robot fails, you know. I guess the object will be dropped.
If you watch 2001 Space Odyssey, then you see what happens with that robot fails.
Yeah, I don't have a good answer. Yeah, please.
So it's all about sort of recognizing humans, yeah. What are kind of common methods right now we're using or in the future for recognizing humans?
How far we got with recognizing the human intent. Okay, no, that we don't. Because, you know, there are different schools in the community, so there are some people who will tell you they can recognize your emotions. I doubt that, but anyways. From my point of view, when I say intent, it's really physical intent, okay? Because that's all what I can recognize. People have tried, we are not the first one, we are not the last one who is trying to do this lifting and cooperative manipulation. There are different philosophies where you, in the past, I don't know, past maybe 3 or 5 years, people tried to use human as the superior, as a controller, and just give commands to the robot. My approach is using them as equal partners. Okay? That assumes that I know somehow how to communicate with the robot. And right now, my communication medium is this object, all right, through which, by exerting certain forces, I'm communicating to the robot what the forces should be. So the robot grasps this and then tests it, you know, and tries to bring the object into some balance. That's the best I know how to do at this point. Okay?
So let me just kind of ask you a big picture question.
Yes, yes.
And you know, there are a lot of challenge problems in there. TAMU was one.
Yes, yes.
Modeling the human system was another.
Yes.
Doing high-dimensional reachability analysis.
Yes.
They're all big open problems that are going to take a
Yes,
long time.
yes. A lot of PhD.
There's a lot of PhD problems. In your opinion, of everybody here,
Yes.
what is sort of the problem? What's the central problem? What's the one that's above all else? Can you state one?
No.
No.
Because they are all connected, Adam, and you know better than anybody else. They are all connected. If you really, look guys, I'm a professor, a quintessential professor, so I'm looking for PhD problems. So I'm happy to find at least 3 PhD problems. And they are all connected, and they are connected in a way that if I stop worrying about them with the human model, how can I communicate with the robot? With respect to the hybrid system and the stability, that's critical, you know, because, you know, all this grasping, as I described to you, and lifting, is a hybrid system, okay? I come, I reach, that's one differential activity. I grasp, that's another, okay? Then I lift, that's another difference. So I have the hybrid system right there in front of me. So I have to somehow deal with the reachability and stability within the reachability. Now, you know, the easy cop out is to say, okay, I'm not going to just like many people do that, right? They say, okay, I will simulate in 2D, and therefore I will have only, for each joint, if I have 2 joints, I have 4, and 2 legs, so I have 8, and that I can solve, and therefore don't bother me. Well, it seems to me that that's a cop-out, and that's why I'm pushing for solving that problem. So, sorry, I cannot say that I would pick one or the other. I think they are all connected, and we all need to work together to solve them somehow as a community.
So rising tide raises all boats.
Yes,
Really is, and
yes, I think
and all
so.
these things.
I met with your dean and I met with your chair, and my feeling is that the robotics is genuinely an interdisciplinary endeavor. And if we collectively want to make success, the electrical engineers, the mechanical, the computer scientists, and even the material scientists will have to work together. There is not one discipline that has all the solution. Even probably some numerical mathematicians have to come into play. So.
Have you applied your conventionals to like finer motor control, such as hand or speech movements?
Speech control?
Like finer motor controls, like hand or speaking, speech production mechanisms?
No speech production, no. That's a very different community. You can serve too many gods, otherwise you don't serve anybody. Yes, the student whose work I presented, Robert Matthew, who is doing the measurement on the muscle and the torque. He is just like similar to Aaron, actually. He is developing. You see, about a year ago, I had a problem with my joints, so I couldn't open jobs. And so we both decided that one interesting problem we can do is designing first you have to measure how much I can hold. And then you can design a little gadget, a little assistive device, but not a big one, a small one, that will connect to my wrist. But based on how much I can, it will just add enough torque. But the critical component there is control, because you want to make sure that you will not break my wrist if it will put enough, too much torque, but enough so that I can open the job. So he's now looking at compensating gravity using some mechanical devices for that. So yes, we are slowly moving towards that, but there is so many open problems. Look up if you are interested.
So I have a question.
Yes.
So when you were discussing the kind of the human and the robot working together, what's the fundamental difference, or is there one, between like 2 robots trying to work together versus a robot?
Okay. So one fundamental difference is that you can model each robot. So you can have a not trivial, but you can have 2 robots that do things in a relatively predictable fashion. It's, many years ago, T.J. Kumar, who I'm sure you will see, he did this 2 mobile robots holding a rod and moving together. So again, interacting to the robot, but one of our biggest investment was that you can model each robot independently, and then you just couple it and it will work. That didn't work. You have to redesign and model the system as a whole, as a dynamical system. Now, the same thing I would predict that you would do with, let's say, two blasters. So that's the two robots. If the human is one robot and you have the other robot, then you have to create the dynamical system of the human. So that's where all these measurements come in. But it could be, now that I'm thinking about it on my feet, that this communication of the intent, going kind of interactively, one can maybe tested on two of us, One robot lifts it and then the other tries to compensate for the lifting. So it could be, and that might be a little bit easier than the human and robot, because you have all the parameters of those robots. But that could be, again, you have to sort of communicate the intent to the other robot. Yeah, go ahead.
I was just wondering, in your opinion, with the current trend in research and advancements, how long would you say it will be before a robot will be capable of using a very complex human model, like the same number of degrees of freedom in the body?
I didn't hear the last sentence, like what?
The same number of degrees of freedom in the human body, very similar.
Oh, you mean that the robot would have the same degrees of freedom as the human?
Yes. Or
So you're asking how long she may think it would be before we could have robots that have similar?
with very similar, not only in how many freedom they have, but also in head, the intensity, the energy each person has.
That's a good question. I think we should ask some mechanical engineers how to build these things so they can tell us. Seems to me, frankly, that you have these humanoids out there online and all that, and they can build certain things, freedom, robot. That's not really, to me, the obstacle. And in fact, in some ways, I don't find it very interesting. I think the more interesting question is, as I mentioned in my book, how can you reduce the degrees of freedom so that for given tasks, of course you want to do it flexibly because depending on what you are doing, but for given tasks, you want to use as few parameters as possible. Efficiency, reliability, simplicity, If you have fewer parameters, things get much more transparent. And then the question whether, I will find that the robot is failing is much easier to detect and analyze and so on.
I think I saw one more question.
Yes, go ahead.
Well, the recent Consumer Electronics Show, we have seen Audi A7.
Speak up a little bit.
In the recent Consumer Electronics Show, we have already seen Audi A7 unveiling its automated cars. Google is set to unveil its automated cars. But when you say that the automated cars generation is about 10 years away from here, where do we say? It was supposed to be a giant leap in the field of science and innovation. But an eminent person like you, when he says that it is 10 years from now.
With this fully automated car, that's what you are asking. It's a look. The transportation department from Washington, the most concern is the safety. All right? Now, there are many, not many, but there are less than 10 different scenarios. So you have a scenario where you have convoys, and there you can have automated system where each car keeps a certain distance, and they all march to the same tune, and nothing is in between, no exceptional. Now, even in the convoys, think about it. So you are transporting, I don't know, goods, the Amazon or whatever, Federal Express, and suddenly a big storm comes, or a big snow, You have to have somewhere in the convoy to somebody to be able to react and propagate that information to these unexpected situations. Those of us who worked in robotics for some years, as I have, one of the biggest challenges, including all the machine learning you have out there, is how do you react to unexpected situations? Okay? So the convoy is a good example under good weather conditions and everything else. But if suddenly you run into an environment where you have a problem, then you have a problem. So that's one place. I understand that in Nevada, there are certain areas where you can, it's like a cruise control. You put on the cruise control, but you still have somebody in that car. The car doesn't drive by itself. I mean, it drives by itself, but it doesn't mean that it's empty, okay? So you have there somebody, okay, who presumably, if there is some unexpected situation, can step in. Remember, if you look at the Google car, they will show you, look, I don't have hands on the thing, but he's sitting there, all right? So, yeah, I am not sure how soon they will, it would have to be in an area of the highway where no other cars are allowed, where you just have these automated cars and under some specific conditions. Because you see, when I'm driving it, you have these, the environment is the unknown. And if the environment is stable and, but look at it. 2 hours ago, there was no rain. Now it's rain. It's slippery, okay? There you go.